right, so that brings us to section 11.2 on calculus with parametric curves. Up until now in this lecture, we haven't done any calculus. All right, starting with tangents, as in tangent lines. Here we have the parametric formula for dy dx. If all three derivatives exist and dx dt is not equal to 0, then dy dx is equal to dy dt over dx dt. So this is a form of the chain rule. And the parametric formula for the second derivative of y with respect to x, if the equations x equals f of t and y equals g of t, define y as a twice differentiable function of x, then at any point where dx dt is not equal to 0, and we're using y prime instead of dy dx, then the second derivative of y with respect to x is equal to the derivative of y prime with respect to t divided by dx dt. And in my experience, this formula tends to confuse people a little bit, so I'd like to show you a couple more details about where that comes from. All right, so what I've done up here is I've written the second derivative of y with respect to x is equal to the derivative of y prime with respect to x. So using that same sort of chain rule idea, which is down here, the derivative of something with respect to x is equal to the derivative of something with respect to t divided by dx dt. By putting y prime in that blank, you get the derivative of y prime with respect to t divided by dx dt. All right, so hopefully that helps. Remember, you can always have this formula in front of you when you're doing problems. All right, so in these two examples, we're going to find an equation for the line tangent to the curve at the point defined by the given value of t, and we will also find the value of the second derivative at that point. Okay, so I'm going to switch back to the tablet. And here we go. All right, so the first question was to find the equation of the tangent line at that point. So for that, we need dy dx. Remember that dy dx is equal to dy dt over dx dt. All right, so first we're going to differentiate y equals tangent t with respect to t. Let me be careful about showing my work here. So derivative with respect to t of tangent t. And then we'll do the same thing with x. All right, so the derivative of tangent t is secant squared t. The derivative of secant squared t minus 1 is 2 secant t times the derivative of secant t, which is secant t tangent t. So we'll make this secant squared t tangent t. Now we can get rid of the secant squared t's. And we're going to evaluate this at t equals negative pi over 4. All right, so we have 1 over 2 times the tangent of negative pi over 4. The tangent of negative pi over 4 is negative 1, so this is equal to negative 1/2. So that is the slope of the tangent line at t equals negative pi over 4. To get the full equation of the tangent line, we need to know what is the point at that value of t. So for that, we're just going to plug t equals negative pi over 4 into our original parametric equations. And if my voice sounded a little funny just then, I was fighting off a sneeze. Okay, so we'll go up here. All right, and the notation that we typically use for this kind of thing is x at pi or negative pi over 4. So that's going to be secant of negative pi over 4, and then we have to square that, minus 1. Let's see, the secant of negative pi over 4, first of all, is the same thing as secant pi over 4 because secant is an even function. And the secant of pi over 4 is the reciprocal of cosine pi over 4. The cosine of pi over 4 is root 2 over 2. The reciprocal of that is just root 2. So that's going to give us root 2 squared minus 1, which is 2 minus 1, which is 1. And then y at negative pi over 4 is the tangent of negative pi over 4, which, as we said a moment ago, is negative 1. So we need the equation of the line with a slope of negative 1/2 passing through the point 1, negative 1. So dusting off our early calc 1 / pre-calc / gosh, all the way back to beginning algebra. The equation of that line is y plus 1 equals negative 1/2 times x minus 1. Oh, are they going to want that in a specific form? Well, they didn't say they did. Oh, what the heck. All right, I'll open up a little more room here. I'll write that in y equals mx plus b form. That's probably how they're going to ask for it in the homework. Okay, so that's going to be y plus 1 equals negative 1/2 x plus 1/2. And now if I subtract 1 from both sides, I get y equals negative 1/2 x minus 1/2. All right, so that is the equation of the tangent line. All right, so what I decided to do here, I wanted to show you a nice picture of this parametric curve along with the tangent line. So in the first set of parametric equations, I put in our curve. Notice I had to put 1 over cosine t squared instead of, that was awkward, secant squared t. All right. And then notice how I input the parametric equations for the line. One cheap way to parametrize a curve where y is given as a function of x is to just make x equal t and then make y equal f of t. All right, so this second set of parametric equations is the easiest parametrization for the line y equals negative 1/2 x minus 1/2. All right, so now I'm going to go to the graph, and you see that the curve is looks like a hyperbola. Actually, I think it's a sideways parabola now that I think about it. And you see the line there looks like it's hitting the curve at the point. Oh, we know it's hitting the curve at the point 1, negative 1. All right. So now let's go back to the tablet because we still have to do the second derivative. Okay, I probably should have left a blank page to do the rest of this problem. Let me get rid of some of this stuff. Okay, we need to find the value of the second derivative. All right, we get that from dy dx. So let me start by reminding you that dy dx, also known as y prime, was 1 over 2 tangent t. All right, which I think I'm going to write as 1/2 cotangent t. All right, so then the second derivative of y with respect to x is the derivative with respect to x of there it is. Okay, I wasn't going to try to hit that pause button. I just needed that sneeze out of there. All right, so it goes like that. All right, so here's what we need to do. We need to find the derivative with respect to t of 1/2 cotangent t. And then we have to divide that by the derivative with respect to t of x, which is secant squared t minus 1. Let's make a little more space down here. Yeah, I really needed a second blank page for this. Oh well, live and learn. Okay, get that back there. All right, here we go. So the derivative of 1/2 cotangent t is negative 1/2 cosecant squared t. And then again, the derivative of secant squared t minus 1 is 2 secant t times secant t tangent t. That's how we got this. All right, and I could possibly clean that up a little bit, but I think I'll just go ahead and evaluate it. All right, evaluating this at t equals negative pi over 4, we get negative 1/2 times the cosecant of negative pi over 4 squared over 2 times the secant of negative pi over 4 squared times the tangent of negative pi over 4. All right, so now I'm going to do something kind of sneaky. Negative pi over 4 is an angle where the sine and the cosine, they're not equal, but they're exactly opposite of each other. They're one of them is negative √2 over 2, and the other one is √2 over 2. So that means their reciprocals are going to be opposites. And then when you square those reciprocals, they are going to become the same. So what I'm trying to say to you is that the square of cosecant negative pi over 4 and the square of secant negative pi over 4 are exactly the same. Okay, so that makes life a little simpler. So I think what we end up with is negative 1/2 over 2 times the tangent of negative pi over 4, which is negative 1. So negative 1/2 divided by negative 2, I believe that is positive 1/4. All right, so that is what they were looking for. The second derivative at t equals negative pi over 4 is 1/4. All right, next problem. X equals cosine t, y equals 1 plus sine t at t equals pi over 2. All right, so first we're looking for dy dx. There goes the bird again. I don't mind when he makes that noise. It's that high-pitched peep that drives everybody crazy, especially the dog. Okay, so we need the derivative of 1 plus sine t divided by the derivative of cosine t, and then we're going to evaluate that at t equals pi over 2. All right, the derivative of 1 plus sine t is cosine t. The derivative of cosine t is negative sine t. We plug in t equals pi over 2. And we get 0, I believe. 0 over negative 1 is 0. So that means the tangent at this point is horizontal. Okay. So to write the equation of the tangent line, really all I need is a y value, but let's not confuse ourselves. X at pi over 2 is cosine pi over 2, which is 0. Y at pi over 2 is 1 plus sine pi over 2, which is 2. All right, so the equation of this tangent line is just y equals 2. Okay, so I think what we're talking about here, this parametrization, this set of parametric equations describes a circle. So this tangent line would be at either the top or the bottom of the circle. All right, now as for the second derivative, let's see. Okay, well, I've got something written on the next page, so I need to, what does this do? No, I don't want to clear the whole thing. I need to do this. Okay, so right here is our dy dx. So dy dx, also known as y prime, is cosine t over negative sine t, also known as negative cotangent t. All right, so we need the second derivative. Let me just jot down the, oh, never mind. I was going to jot down dx dt, but that's easy enough to just get again. Okay, second derivative of y with respect to x is the derivative of y prime with respect to t divided by dx dt. All right, so we need the derivative with respect to t of negative cotangent t divided by the derivative with respect to t of cosine t. All right, so that is going to be cosecant, whoops, cosecant squared t divided by negative sine t. We will evaluate that at t equals pi over 2. And I believe that's going to give us 1 over negative 1, which is negative 1. So this must be the tangent line at the top of the circle because the curve is concave down there. All right, and that's going to do it for that batch of examples. So to wrap up this lecture, we're going to go back to the presentation and talk about the length of a parametrically defined curve. So you should have done something along these lines toward the end of Calc 1. If a curve C is defined parametrically by x equals f of t and y equals g of t for t in the closed interval from a to b, where f prime and g prime are continuous and not simultaneously 0 on the closed interval from a to b, and the curve C is traversed exactly once as t increases from t equals a to t equals b, then the length of C is given by the definite integral from a to b of the square root of f prime t squared plus g prime t squared with respect to t. All right, so we will do one example of finding the length of a curve, and it's going to be this one: x equals t cubed, y equals 3t squared for t between 0 and the square root of 3. Switching back to the tablet one last time. All right, first I'm going to jot down that formula so I remember exactly what it is I need. So L, the length of the curve, is the integral from a to b of the square root of f prime t squared plus g prime t squared dt. All right, so in this case, that's going to be the integral from 0 to the square root of 3. All right, the square root of f prime t is 3t squared, right? And the derivative of y is 3/2 times 2t, so that's 3t. So 3t squared. All right, so usually the challenge with these is just figuring out how to do the integral. I don't think this one ends up being too hard. All right, so this is the square root of 9t to the 4th plus 9t squared. Okay, now we're going to do a little bit of factoring. Let's see. So integral 0 to the square root of 3. We have the square root of 9t squared times t squared plus 1. All right, so now I can break up that radical. Notice that t is positive on this interval, which means when I talk about the square root of t squared, I can just make it t. I don't have to make it absolute value t. All right, so the square root of 9t squared is 3t times the square root of t squared plus 1. All right, so I believe what we need here is a basic substitution. We're going to let u equal t squared plus 1, which is going to make du 2t dt. All right, what we want is a 3, not a 2. So let's just get rid of the 2 and we'll replace t dt with 1/2 du. And then finally, you know me, I like to replace my t limits with u limits. So if t is going from 0 to the square root of 3, and u is t squared plus 1, that means that u is going to go from 1 to root 3 squared is 3. 3 plus 1 is 4. All right, so new and improved integral. Let's see, we're going to replace t dt. Well, let's get that 3 out of there. Oh, let me just rewrite this integral. So it's going from 0 to root 3. 3t times the square root of t squared plus 1. Okay, so that's now going to be 3 times 1/2 times the integral from 1 to 4 of the square root of u du. In other words, 3/2 times the integral from 1 to 4 of u to the 1/2 du. So we'll use good old-fashioned backwards power rule. Oh, this works out beautifully, doesn't it? The integral of u to the 1/2 is 2/3 u to the 3/2. So we're going to plug in 4, plug in 1. Goodbye, 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 goodbye. All right, so the length of this curve is 4 to the 3/2 minus 1 to the 3/2. 4 to the 3/2 is 8. 1 to the 3/2 is 1. The length of this curve from t equals 0 to t equals the square root of 3 is exactly 7. And that is going to take care of sections 11.1 and 11.2. We'll see you next time. There is only one more lecture to go. Take care.